Welcome back. So in this video, we're going to focus mainly on computing the capacity of a spiral column and kind of showing you the mechanics on how they determine, the stress is based on an axial stress, how much stress goes into the spiral itself. And so you'll be calculating a volumetric calculation, a volumetric reinforcement ratio. It's a little bit different of an animal, but if you just kind of remember, think in circles and think in cylinders, and hopefully this will make a little bit of sense to you. So without further ado, we'll get ourselves going there. Thanks. General P0 formula, but this kind of defines spiral columns and how we are able to figure out the strength of a spiral column. Okay, so what happens is in a spiral column, and I haven't drawn all of them, but pretty much what's going on here is I have a spiral and it's kind of wrapping around, it comes down this way and it comes down this way and it just kind of loops its way down, forming that. But we're going to look at, basically one little circle of this thing, that in a column I'm applying a stress F1 acting down this way. And then, Poisson's ratio says that, well, if I take a column and I try to squeeze it this way, the lateral dimension wants to open up in response, okay? And so it's that opening that pulls on this confining steel, which creates a confining pressure that we're going to call as F2, okay, for a particular face like that. Okay, so for a spiral column, we're going to go with this assumption that we have a circular column. Okay, we've got 6 longitudinal bars, diameter of D. Okay, the core diameter is this DC value. All right, so what happens in a spiral column is that we basically only look at what's inside of the confining steel. Anything outside of this, when it tries to get pushed out, is assumed to just kind of break off and spall off. So this DC parameter is going to be very, very important to us as we look at. So what we're going to do is we're going to take a look at, for one given spiral loop on this thing. Now again, this isn't all in the same plane. This thing's kind of in there kind of slanted, if you will, that for an axial load F1 acting down, I can do a sum of forces X on the free body diagram of this thing, all right? So I've got my confining pressure F2 that's pushing on the steel, and then the forces in the steel bars are going to, respond in order to try to balance it, all right? And so we're going to take ASP times FSP, which is the stress in the spiral multiplied by the area of the spiral, and I have 2 of those because I cut the spiral in 2 places. Okay, and then that the diameter from here to here is DC, which was the diameter of the core of my column, and I can do a sum of forces X in this, okay, which basically says I'm going to take 2 times ASP, which is the area of the spiral, times the stress in the spiral is going to be equal to then the projected area of F2 times DC on this particular area times the spacing. Now that S characteristic, the S that's here, if you look on our spiral, that would be the distance that exists, say, between here and the next one up at the same point. So that's what our S is. Okay. Now, okay. So if we rearrange, then we can say that the confining stress in this is going to be 2 times ASP times FSP over DC times S. Okay. Where in this case F1 is the axial stress in the core, F2 is the confining stress acting on a hoop, ASP is the area of the spiral reinforcement, FSP is the stress in the spiral, and DC is the diameter of the core, and S is the pitch of the spiral. And again, there are prescriptions on what the pitch is allowed, and we talked about that in the last video as well. Okay. All right. So what we can do is we can turn around and we can say, well, let's figure out what this, see if we can make some adjustments and calculate a spiral reinforcement ratio. Okay, now if you remember back in Flexure, we were doing rho equals AS over BD. This one's a little bit different, okay, in that we're going to take the volume of the steel that we have, okay, and we're going to divide that by the volume of the concrete core. Okay, and now this is the amount of material that's associated. Again, we're looking at just one loop of this. So you get a half of a pitch spacing below and a half of pitch spacing above. That's why it's a full pitch spacing S. Okay, and so if we do that, we're going to take the area of our spiral, okay, and we're going to multiply that by pi DC. Okay, that will be kind of the equivalent of our volume of steel, and then we're going to divide that by then the area of the core, okay, which would be pi over 4 DC squared, and then multiplied by the pitch spacing. This is all of the concrete that's associated with one complete loop of a spiral as we do that. And if I do the math and do some simplification of this, we can say that the reinforcement ratio for the spiral then is going to be 4 times ASP over DC times S. Okay, and if we kind of look at the way we want to write this, then we're going to say that F2 then is going to be 1/2 of rho S times Fy. is where that's kind of coming from. So it's not really a BD kind of thing. It's kind of it's a volumetric. So we're pretty much multiplying by some other value over some other value to get a volume and a volume here. And that's kind of the way that the spiral is considered. So if I know my reinforcement ratio, then I know what my limiting stress in F2 can be before I fail the steel. And again, this encompasses, this rho S encompasses the size of the spiral, it encompasses the pitch spacing and the diameter of the spiral and the column itself. So that becomes our F2. And so that's one way that we can kind of start to kind of design this stuff. All right, now what we want to look at then is, well, what's the relationship between F1 and F2? So again, what we've done is we've come in and said I'm applying some sort of F1 in this direction and I'm pulling out something for an F2 in that direction. Okay, and so there's an interaction that happens in this. Okay, when F2 is 0, F1's limit is 0.85 F prime C. Okay, that's just the pure compressive value. That's that Whitney coefficient again. This 0.85 F prime C shows up over and over and over again in our calculation. Okay, but what we find is that as I increase F2 and provide more and more steel this way, okay, I can increase F1. All right, so this is the unreinforced position. That once I get to that limit, I fail it. Okay, but then as I start to increase F2, you can see that I actually start to gain strength. Okay, and so the equation of this line is said to be F1, which is 0.85 F prime C plus, based on experimental research, about 4.1 times F2. Okay, and that jives pretty well with that prediction model that we had. Okay. Okay, so what happens is that prior to crushing, you know, before the concrete reaches its axial limit, we had our axial formula, that P0 formula. Now again, we're doing it for a spiral, okay, and well, we're doing P0. We haven't declared spiral or tie yet, but we have 0.85 F prime C times the gross area plus AST Fy. That's what we had before crushing, okay, and then after, as we reach the end, I end up with, you know, after you've spalled off the side of this thing, I get my F1 times the area of the core. So that's the load that can be transmitted down the middle of the column. Okay, and then plus my area of steel times Fy is kind of our after relationship. And so we can kind of start to rearrange some things here and do a little bit of algebra and a little bit of math. Now what you notice is AST-Fy and AST-Fy are on both sides. Those guys will cancel out. Okay, and so when I do that, I'm left with this term being equal to F1 AC. Okay, and so if we go through and we do that, this F1 equation, I can come back up and I can grab this guy and throw him down into the equation here. All right, so we're just doing a little bit of algebra at this point. 0.85 F prime C AG is going to be equal to 0.85 F prime C plus 4.1 F2 multiplied by the area of the core. Okay, and so very quickly we can kind of come back in and we can kind of make some arrangements for stuff, and notice that F2 is in here, so now I can take my formula for F2 and I can throw it in here, and so there's my reinforcement ratio for the spiral again, and again we assume that it yielded. Okay, and if I divide AC through and do a little bit of shuffling of things on this, I get 0.85 F prime C AG over AC. Okay, and then I can do a little bit of factoring out on this thing, that if I divide this by 0.85, okay, or subtract it over and do some factoring and a little bit of rearrangement, I can actually solve for the reinforcement ratio rho S out of this equation. And when I do it, okay, I get the equation 0.415 AG over AC minus 1 multiplied by F prime C over Fy. It becomes the equation, okay? And so to be able to get my capacity on this thing, is I can figure out what my reinforcement ratio needs to be by taking the gross area, the core area, which was the diameter of the core, or how wide around your spiral is going to be in your diameter, concrete strength and steel strength, and I've got the rho S that's needed to be able to develop that. And so that's why we start to kind of define this. Okay, and so what they say then, ACI actually takes this formula, okay, and this is called the volumetric reinforcement ratio. So you're going to take that volumetric rho S, and it has to be greater than this number, 0.45. Okay, so again, you see they cheated a little bit here. Okay, that's my 25.7.3.3, AG over A naught H, okay, minus 1, okay, and then F prime C FYT. It's written a little differently, but this is where it's coming from, all right? So our area of the core is the theoretical, this is how they're going to calculate, they're going to tally it up for the particular column. But it's basically, it's that core, that critical area that's effective for the capacity. And then of course there's a limit on FYT as a maximum of 100,000 psi. So you can't go put a huge number, an ultra high strength in here, like 1,000,000 psi or something ridiculous, and zero this thing out and make it, oh, rho can be anything. It doesn't work that way. So they do put a hard cap on this, recognizing that things change at higher stress values. Okay? All right. So that's kind of how the interaction diagrams kind of work and how we start to kind of set up our bases. All right. We'll go ahead and we'll stop this one here. And in the next video, we'll get into kind of drawing some of the pictures and some of the Whitney diagrams that help us further calculate those points. So with that, it's kind of a little bit of a theoretical setup, kind of where things are coming from and how we start to handle spirals, and then what an interaction diagram actually looks like in the different points. And then in the next video, we'll actually start to put it to work. So anyway, as always, I hope it's made sense to you. Leave us some comments down below. Please be sure to like the video, and as always, subscribe to the channel. We greatly appreciate it. So have a wonderful evening, and we will talk to you all next time. Happy engineering. All right, so with that, we'll end our discussion on kind of how you compute the spiral column capacity and how you can come up with this reinforcement ratio for a spiral column, that volumetric reinforcement ratio here. So for now, we'll end the discussion here. I know it's a fairly short video, but I just decided to go ahead and split this out into a couple of parts to make it a little bit more digestible. And I hope it meets with your approval. So as always, if you'll leave a comment down below, and like and subscribe to the video, and then as well and subscribe to the channel, of course, we would greatly appreciate it. And we will see you momentarily back when we get into interaction diagrams. So I hope this all makes sense. Thanks. Bye. Happy engineering.